Hello, and welcome to our presentation for the Project Tango robot for Capstone 1 Fall 2016, presented by Yihan Chen, Dalton Daniel, Bella Durand, and Jacob Maccabee. Google is developing Project Tango, tablets and smartphones that include 3D cameras that can map out its surroundings and be loaded into multifunctional apps. It uses Google's Android technology with the added component of a 3D camera. Project Tango's 3D camera provides another example of the tech industry's advancements in computer vision, and combined with speech recognition and artificial intelligence, the potential for the creation of real digital assistants is becoming possible. A previous capstone group was tasked to create a robot integrating Project Tango technology. They built a base with 3 multi-directional wheels and a battery pack, all controlled by the Project Tango tablet and an Arduino. However, the robot was a bare skeleton with exposed wiring and metal structure, and lacked any arms for interaction. Therefore, the scope for our project was to create arms allowing the robot to be more expressive and interactive, and to manipulate small objects, as well as create a plastic shell that covers all of its exposed metal structure, and as well as giving it a aesthetically pleasing silhouette and design. Similarly capable robots cost upwards of $6,500. Our budget for the arms and body targeted $700, with an additional $300 for reusable tooling costs.
For the arms, we used a 6-servo model for maximum expressiveness. That would be 2 servos for the shoulders, 1 for the elbow, a servo for rotation above the elbow, a servo for rotation below the elbow, and a final servo to operate the gripper. To make sure the servos were adequate, we ran testing through SOLIDWORKS Motion, which was able to move the servos independently and analyze the required torque for the movement. From this analysis, we found that all the output torques, with the exception of the first 2 shoulders, were adequate. To deal with this, we added a gearbox to the first 2 servos that would enable it to lift larger loads.
Given the analysis of the gripper, it was determined that it could lift 1 pound at least before fracturing. Analysis performed on the gripper found it could easily lift at least 1 pound without experiencing failure. Thus, the design as it stands was chosen for the project. The skeleton design utilized existing stock materials, reconfigured to slim down the profile and weight. A sturdier platform was added to mount the arms, and the tablet mount was simplified. The body panels were designed to be vacuum-formed ABS plastic, presenting a sleek and polished appearance with a minimum of weight and cost. The cost of manufacturing the parts is minimized by using forming and wooden molds, eliminating the cost of more complex molding processes. The mold design takes advantage of MSU's Makerspace CNC capabilities, designed to be the CNC machined with a shop-bought desktop from blocks of fiberboard. The shell panels are designed to be easily removable, with a combination of threaded fasteners for a secure lock and drop-in connectors for easy removal. The design utilizes 3D printed attachment lugs bonded to the shell, creating a modular interface for easy disassembly or changes. Analysis of the shell focused on the possible loading it might undergo during use or misuse. It was found that the shell provided sufficient strength in most circumstances, but would be insufficient to support the full weight of the robot if picked up. It was decided to leave the shell weaker to minimize cost and weight for this prototype. Instead, a lifting handle was added to allow for intuitive handling of the robot without risking damage to the shell. When manufactured, the robot should be both expressive and aesthetically pleasing. Integrating with Project Tango software, it can act as a personal assistant that can navigate around a given space. You can enter your house, plug in your phone or your tablet, and it can follow you around, acting in accordance with the environment it's in. With the design phase of the project complete, the first 3 months of the spring semester will involve the manufacturing and assembly of the arms and shell. Testing will be performed throughout the semester in incremental steps. The first test will begin when the first servos and brackets are assembled and when the first mold is milled. The final testing procedures will be finalized by mid-March. Assembly and prototype rollout should be completed a month before the design fair to allow time for extensive programming and testing.